morning, this is B. Naresh, working as assistant professor in EC department. Today we are going to discuss definitions and terminology on module 5, that is FET amplifiers. So in this session, we are going to observe some of the definitions related to this FET amplifiers. So the first one is, what is JFET amplifier? So in generally, we have the two types of the FETs. One is called as JFET, and here it is called as junction field effect transistor. Another one it is called as MOSFET, metal oxide semiconductor field effect transistor. So then these FETs is also we can use as a amplification process to improve the signal strength in terms of voltage or a current or a power. So hence these FET amplifiers to provide excellent voltage gain with why? Because of that, it having a very high input impedance. The reason is why it contains a high input impedance means, based on the construction of the JFET amplifier, the input means the gate is biased with a reverse voltage, hence it offers very high input impedance. So hence we are going to choose, this is the JFET is acts as a amplification process with an excellent voltage gain, means it provides a high voltage gain parameter. So we know that the gain is the ratio of output voltage to the input voltage. Now define transconductance. So here the transconductance is represented as GM. So in generally the reciprocal of impedance, the reciprocal of the impedance means this is 1 by Zi, that is called as transconductance. And here we are going to define this transconductance. So hence it is a defined. So generally we know that the input impedance means it is a ratio of input or voltage to the input current. So suppose if you want to write the impedance at output side, it is defined as it is a ratio of output voltage to the output current. So hence that is defined as V by I. From this, we are going to observe the transconductance. It is the reciprocal of input impedance. Hence, it is defined as it is the ratio of current to the voltage. And if you want to define to this FET, so in a FET we know that it contains the three terminals: source, drain, and gate. Based on the construction, the most of the cases we are taken as the drain is the output side, and gate is taken as the input side. And here we are going to find out. So hence the current means that is the reason it is defined as the ratio of the change in drain current to the change in gate to source voltage. So hence this transconductor, and again this transconductance is derived from the transfer characteristics. So hence, if in a field effect transistor, if you want to draw the transfer characteristics drawn between gate to source voltage and drain current. And if you observe the transfer characteristics, then we know that when VGS is a 0, it offers a maximum drain current, that is represented as IDSS. Whenever a VGS is decreased from the 0, the drain current is also decreased towards to a minimum. And at this point, we know that this is VGS off state. So hence, now we need to define how this drain current changes with respect to the change in gate to source voltage. That define means this is reciprocal of the slope. So hence that reciprocal of the slope is also defined as the transconductance GM. So hence this GM is represented as the rate of change of drain current to the rate of change of the applied input voltage between gate and source. Now, similar to that, we need to define drain resistance. So here the drain resistance is defined as RD. So in general, again, this drain resistance is absorbed from the drain characteristics. So if you want to draw this drain characteristics, the drain characteristics are plotted between drain to source voltage and drain current while making the VGS is constant. Let us assume that. So when VGS is a 0 and the VDS is increased from the 0, then your drain current is exponential or linearly increases towards a maximum. And then at this point, at this switch voltage, and this is called as the pinch of voltage. After this pinch of voltage, the drain current becomes saturated or becomes constant, and this is observed when at VGS is 0. And this region, we know that this region is called as a linear region, and below this zero line, it is represented as cutoff region. And from this VP, it is represented as saturation region. Clear? So hence, we are going to observe. So here the drain resistance from this drain characteristics, hence that is the reason. So generally, we know that resistance means it is a ratio of voltage to the current. So from this drain characteristics, what is the input voltage here? It is taken as a VDS, and current is I. So that is the reason. It is defined as the change in drain to source voltage to the change in drain current at a constant. So we take as a constant gate to source voltage. So hence this RD is defined as the rate of change of a drain to source voltage with respect to the rate of change of a drain current, that is represented as dou ID at VGS is constant. At VGS is constant. Now similar to that, the next one is define common source amplifier. So based on the field effect transistor configuration, we have the 3 terminals. So one is represented as source, drain, and gate. So then we are making this. In this case, the source is a common for drain side as well as the gate side. So that is the reason. So a common source amplifier is also used as a voltage or a transconductance amplifier, in which, so we take as this source is the common for input side as well as the output terminals. So means, so when the source is a common, gate is acts as the input, drain is considered as the output terminal. Now define common drain amplifier. So yeah, a common drain amplifier. It is also called as a source follower. So why? Because of that, the drain is a common, drain terminal is taken as a common. So hence gate is acts as the input, and source is acts as the output terminal. So from that, so we know that the source is always envisage the charge carriers to allow the conduction. That is the reason. So we are again measuring the quantity across the source. So hence it is taken as, it is called as a source follower, in which the drain terminals are made common to input. The input terminal is a gate as well as the output terminal is source. So similar to that, define common gate amplifier. So what is a common gate amplifier? Means, so in this case, gate is acts as a common terminal, source is the input, and the drain terminal is the output. So hence, a common gate amplifier used as a current buffer or a voltage amplifier, in which, so we consider that the gate is common to both the signals input side and output side. So hence, the input is considered as source and output terminal is considered as drain. Define current gain for common drain amplifier. So at this point, it is a day means common drain means. So let us consider a effect JFET, and let us consider this is gate. So here I'm going to make the drain is a common. So here I consider the source. So means, and this is input, and output is measured across the source terminal with respect to the drain. So generally, if you want to define any gain, it is a ratio of output parameter to the input parameter. So here the output parameter is measured across the source here, and input is measured across the gate. So hence it allows the source current. So the current is flows from drain to source, and this is source current IS, and the gate current is IG. So hence it is defined as, so the gain here it is defined as source current is IS to the IG. So this is the current gain of the common drain amplifier. Now define the voltage gain of for common drain amplifier. So generally the voltage gain means it is a ratio of output voltage to the input voltage V out by V input, that is gain parameter for common drain. So if you consider this common drain, so the output is measured across the source, hence the voltage across the source terminal to the voltage across the input terminal is gain. So hence it is defined as the ratio of the output source to drain voltage along with to the gain to drain voltage. So this is the gain parameter. So in terms of voltage for this common drain amplifier. Then define input impedance for common drain amplifier. So again, if you consider, let's take gate. When this is the source, this is the drain, and here I'm going to draw the. So this is input voltage, and then output is taken from source to drain. Now we are going to define the input impedance Zi, or it is also called as Ri. Means it is defined as it is the ratio of input voltage to the input current. So from this configuration, so if you observe, the input is passing through the gate, hence the input is represented as voltage across the gate, and input current, here the current is represented as gate current, that is IG. So hence it is defined as it is the ratio of input gate to drain voltage. So means this is gate to drain. So we can also write VGD to the input gate current, that is IG. So this is Zi, or nothing but a input impedance for common drain amplifier. Define output impedance for common drain amplifier. So similar to that, now we need to consider, now means we need to observe the output impedance for a common drain amplifier, and let us consider this is source, and output is measured across the source, and now we apply the input signal. Now we need to find out the output impedance, means we can write the Z naught means, or it also represented as R naught. So it is defined as it is a ratio of output voltage to the output current. So from this common drain amplifier, if you want to find out output voltage, so the voltage is measured across the source terminal to drain terminal, and output current is IS. So hence the output voltage is represented as the voltage from source to drain terminal to the source current, how you know it is IS. So hence it is defined as is the ratio of output source to drain voltage to the output source current, that is IS. So this is output impedance for common drain amplifier. Now define current gain for common source amplifier. So now we need to draw the common source amplifier. Let us take this is JFET and source and a drain. Common source means the source is common for input side and output side. And based on this, gate terminal acts as a input and output is measured across the drain terminal with respect to the source terminal. So now we need to define the current gain, means the current gain is represented as A. So we know that it is the ratio of output current to the input current. So what is the output current? So here we are measuring the current is drain current, output current is the drain current, hence it is ID. And input current is the input voltage is passing through gate, hence it produces the gate current, that is IG. So hence the current gain for a common source amplifier is defined as it is a ratio of drain current to the input gate current. Now define voltage gain for a common source amplifier. So now for this case, now I am going to consider a JFET and now we need to consider the common source amplifier. Hence this is the drain, source, and input is passing through the gate. And let us say this is Vi. It is biased with the VDD, and output is taken from the drain to source. Let us take this is Ig, and the drain current is ID. Now in between the voltage is represented as VDS, and input voltage is measured between gate to source. Now we need to define the voltage gain. So generally it is defined as it is the ratio of output voltage to the input current. So from this, what is output voltage? The output voltage is measured across the drain with respect to the source, hence it is defined as VDS to the input voltage is passing through the gate with respect to the source, hence it is defined as VGS. Hence it is the ratio of output drain to source voltage to the input gate to source voltage. That is the voltage gain for common source amplifier. Now define input impedance for common source amplifier. So let us consider the JFET again. This is drain and source, gate. Now we consider the common source Vi. Drain is the bias with the VDD, and output is measured across the drain and the source. It allows the drain current, that is ID. Now we need to define the input impedance Zi or Ri. So means it is a ratio of input voltage to the input current. If you observe this input voltage, what is input voltage? The input voltage is between gate 2 and the source, and the input is passing through the gate current, hence it produces the gate current. That input current is Ig. So hence it is defined as the ratio of input voltage to the input current, means gate to source voltage to the gate current. So define output impedance for a common source amplifier. So again I am going to consider this common source amplifier. This is gate terminal. Drain is the bias with the VDD. So source is the common for input and output. Now we need to define the output impedance, means Z0 is also represented as R0. It is defined as it is the ratio of output voltage to the output current. What is the output voltage? The output voltage is a measure between drain to source, hence it is represented as VDS. And the output current, the current is a measured across the drain terminal, hence it produces the drain current, that is ID. So hence it is defined as it is a ratio of output drain to source voltage to the output to drain current. Now define the current gain for common gate amplifier. Now we need to consider the common gate. So in a common gate, the gate is a terminal is acts as a common for input and output. Hence, source I taken as input side and the drain I consider for output side. And the gate is a common. Let us consider the input is passing through the source. Output is taken from the drain. Hence, it allows the drain current ID. Now, we need to find out this current gain means it is a ratio of output current to the input current. And if you observe this a common gate amplifier, the output current is measured across the drain. Hence, it is defined as the drain current to the input current. It means input voltage is passing through the source. That is the reason defined as IS. So hence, it is defined as the ratio of drain current to the input source current. Now define the voltage gain for common gate amplifier. So similarly here, again I'm going to consider a common gate amplifier. This is gate, source and a drain. Input is passing through source. Output is measured across the drain. Now we know that the voltage gain means it is a ratio of output voltage to the input voltage. If you observe this one, the input voltage means the voltage between source and a gate, and the output voltage means the output voltage measured drain and gate. So this is VDG. Hence, so we can write the voltage across the drain with respect to the gate to the input voltage means the input voltage is passing through the source with respect to the gate. So it is called as the voltage gain. So hence it is defined as the ratio of output drain to gate voltage to the input source to gate voltage. Now define the input impedance for common gate amplifier. So to observe this input impedance for this common gate amplifier, let us consider source, drain, and in common terminal is the gate. Let us take this is input voltage and output is taken from drain terminal. Let us this source current is the flows. Now we need to write either ZI or RI. It is a ratio of input voltage to the input current. From this configuration, from this common gate amplifier configuration, so what is input voltage? The input voltage is between source and the gate, that is represented as VSD, means input voltage is passing through source to gate terminal. And the input current, what is input current from this configuration? The input current is acts as a source current. So this ratio is called as input impedance. So hence it is defined as the ratio of input source to gate voltage to the input. This is source current. This is input source current. Now define the output impedance for common gate amplifier. So for this case, again we need to consider source, drain and the gate. Gate is a common input voltage and this is output voltage. So here we are representing that. So output impedance means Z naught or R naught. It is defined as output voltage to the output current. What is output voltage? The output voltage is measured between drain and the gate. It is represented as VDG. And output current is measured across the drain current, that is represented as ID. Hence, it is defined as the ratio of output drain to gate voltage to the output drain current. Now define MOSFET. So here the MOSFET means the metal oxide semiconductor field effect transistor. So to fabricate this one, we need to use these metals as well as a insulator metal and semiconductor, and can be mostly used for switching and amplifying the electronic signals in the electronic devices. And recall the working principle of MOSFET. So to understand this, the working principle of MOSFET, so first we need to understand the construction. Let us take this is substrate or a base. It is also called the semiconductor. Then we are diffusing these are the materials. So if you are diffusing the entire material, the substrate should be P. Then let us take this is N wells. So one well is called as the source, one well is called as the drain. Then next we are diffusing the oxide, that is silicon dioxide, a insulating media. Then after that we placing some metal. This is the metal is actually conducting, and for this we are applying terminal is gate. Now, so this is the channel. To allow the charge carriers from the source to drain, here we need to apply some amount of the force. So here means that we need to apply. So the source is N type. The majority charge carriers are electrons, and this is negative charge particles. So for this negative charge particle, if you want to repel these negative charge particles, we need to apply the same amount of energy. Hence, here I am applying a positive energy. So then based on this applying field, so it means it looks like your capacitor principle. This is a metal conducting plate, this is a metal. So here we have the input. So when we are applying a positive energy here, it generates a negative, and again it generates the positive conduction. Here it generates the negative plate. So hence a negative ions will be established here. Due to this establishment of negative charge ions here, then the charge carriers are repelling from the source to drain to allow the conduction. And for this case, let us take, so here to allow the charge carrier to repel the charge means we need to apply some amount of the energy between the source and the drain. So hence the source is biased with a negative pole of the battery with respect to the drain, and this is called as a VDD biasing, plus and minus. So or it is also called as a drain to source voltage. So hence we need to change this biasing voltage between the drain and source. Hence the number of charge carriers are repelling from the source to drain with the applied gate voltage also. So that is the reason. The MOSFET works by the width of the channel along with the charge carriers flow. So in this case, the charge carriers enter the channel source and exit via the drain. And this width, this is called the width. The width of the channel is controlled by how much voltage we are applying on the gate. So based on this applied voltage of the gate, this will be controlled here. Due to that, the number of charge carriers are repelling from the source to drain to allow the conduction from drain to source. So what is P-channel MOSFET? So in a MOSFET, we have the two types of the MOSFETs. One is the P-channel and N-channel. So in this case, we have defined this P-channel MOSFET as a P-channel region between source and the drain. So hence, the drain and source are heavily doped P plus region, and the body substrate should be N type. So here the body substrate should be N type. So similar to that, what is N-channel MOSFET? So here N-channel MOSFET means the source and the drains are defined with the N-channel. So hence the N-channel MOSFET has a N-channel region between source and the drain. So in this case, the source and the drain materials are doped with the N plus region, and the substrate should be opposite material, that it becomes a P type. Now again, so in the FET amplifiers, again we have the one more special purpose devices are there in module 5. So in the special purpose devices, apart from that what we discussed in modules like semiconductor some BJTs. Right? Apart from that, we have some special purpose devices like the one is a zener diode, like a varactor diode and tunnel diode. So here, what is actually a xenon diode? So what is the difference between a normal diode and a zener diode? So why we go to utilize this zener diode? To understand this one, so if you recall the principle of PN junction diode, and based on the approaching of the biasing methods to PN junction, the PN junction works under only the forward bias, means it allows the conduction in only the forward bias. Whenever we are applying the reverse voltage to the PN junction, then the PN junction diode is acts as a non-conducting state. So hence, to utilize diode reverse bias also, we are going to they designed a heavily doped material compared with a normal PN junction diode, that is called as a zener diode. So hence, here the zener diode is a type of a diode. It allows the current to flow not only from the anode to cathode but also in a reverse direction also. So when the zener voltage is reached. So list some applications of zener diode. So what are the applications? So where we are going to utilize? Most of the cases, the zener diode is utilized in to define the voltage regulator concept or linear power supply sources. So hence, zener diodes are widely used to generate low power stabilized supply rails from a higher voltage to provide the reference voltages for circuit. So especially that is used in the stabilized power supplies, means in RPSs. So we need to use this zener diode to maintain a constant DC voltage. Define a voltage regulator. So means the function of this voltage regulator to maintain a constant output voltage irrespective of the change in supply voltage or the change in load. So that is the reason. The function of the regulator is to provide a constant output voltage to a load connected in parallel within a spite of the ripples in the supply voltage or the variation in the load current, and the zener diode will continue to regulate the voltage. So means that, so irrespective of your changes either in the input source or the load side, we need to maintain a stabilized output voltage, that is called as a voltage regulator. So define zener breakdown. What is zener breakdown? When a reverse voltage is applied to the zener diode, so we know that in an avalanche breakdown like that, in a normal diode, when a reverse bias, reverse voltage increases in a for a PN junction, a particular reverse voltage, it breaks down the diode operation. So hence here also, when a reverse voltage is applied to zener diode, it causes very intense electric field that appears across a narrow diffusion region, such that electric field is strong to enough to pull some of the valence electrons in the conduction wire by breaking their covalent bonds. So next, another one is another special type transistor is UJT. So define UJT. So here the UJT abbreviation is a unijunction transistor, means it contains only one PN junction. So then most of the cases it acts as a one switch. So similar to that, define varactor diode. What is a varactor diode? Means it is also called as a varicap capacitor. So means it looks like. So means this is actually capacitor. Varactor diode means a diode. So this is the symbolic representation. So this is a variable capacitor, varicap. It is also called as a varicap. So in this case, a varactor diode is a PN junction diode whose capacitance is varied by varying the reverse voltage. Means this varactor diode works under the reverse voltage only. So first means we need to understand this capacitor, the capacitor principle. So based on the capacitor principle, this works like a varactor diode. So in generally, we know that the diode is under the reverse bias. It offers a transition. It means it acts with some capacitance. Why? Because of that, when this is the PN junction, if you apply the reverse voltage, then what happens? It increases the depletion width. So from this, we can define this is equal to so dq by dp, the rate of change of charge with respect to the means rate of change of applied voltage. So now define SCR. So here the SCR is a silicon control rectifier. It is also a semiconductor control rectifier. It is a four-layered solid state controlling device. It also contains the three junctions. Those are represented as J1, J2, and J3. So means the symbolic representation of this one. This is the anode and the cathode. It is gate. So what are the define the modes of SCR? So we are on the three modes of SCR. One is a forward blocking mode, that is also represented the off state, and one is forward conduction mode, the state is represented as the on state. The next one is the reverse blocking mode, that is off state. So these are the three modes of operation for SCR. Then define forward blocking mode. What is a forward blocking mode? So means let us take the internal structure of this one. So it contains P, P1, N1, P2, and N2. So this is represented as the junction J1 and J2. This is junction J3. So this forward blocking mode means so we need to apply this is the anode and this is cathode, and nearby this junction we have this a gate terminal. So now we are going to apply a forward biasing. Forward biasing means anode is connected to positive pole with respect to the cathode. So let us take this is positive and a negative. So what happens due to this? So means we have the three junctions J1, J2, and J3. Due to that, due to this approach of this biasing energy, J1 becomes the forward bias, and J3 is also junction 3 is also become the forward bias, but J2 becomes reverse bias. So if the J2 becomes the reverse bias means in this at this junction the depletion region is increases. Hence, it does not allow the movement of the charge carriers from the cathode to anode. Hence, does not flow the conduction from anode to the cathode. So that is the reason. At this point, the SCR, the state is represented as non-conducting state or off state. That mode here it is called as the forward blocking mode. Now define reverse blocking mode in a SCR. So similar to that, so this is the internal construction again. Let us take this is the P1 material, N1 material, P2 material, and N2 material, and junction J1. This is junction J2 and J3. So we are applying the reverse means this is let us take this anode is connected to a negative pole of the battery with respect to the positive pole. So means this cathode is connected to the positive pole of the battery, and across this nearby this we have the gate terminal. Now see what happens when a reverse bias is approached to the anode and the cathode. Based on this, we know that J1, so J1 becomes reverse bias, and J3 is also becomes the reverse bias. So why? Because of that, this anode positive P type is connected to negative pole, then we know that it acts as a reverse bias. And but J2 becomes forward bias. But what happens? J1 and the J3 is acts as a reverse bias. Hence, there is no movement of the charge carriers from the cathode to anode. Hence, there is no flow of conduction or charge from anode to cathode. And at this point also, then this SCR is acts as a non-conducting state. Hence, this is called as a reverse blocking mode in SCR. We list some applications of SCR. So we are having some applications. It can be used as a rectifier or lamp dimming applications, some power regulators, and some motor controls. We are going to use this as here. So now define tunnel diode. What is the tunnel diode? So tunnel diode is also a heavily doped semiconductor device. It works on the principle of tunneling effect. It is also called as Saki diode. Define tunneling effect in a tunnel diode. So in this case, to understand this one, the energy barrier is greater than the barrier. So then the quantum mechanically there is a non-zero probability the particle with energy less than the energy barrier will cross the barrier as it tunnels across the barrier. So means based on the energy band diagrams, let's say this is a p-type material, and so if you're taking some the pure semiconductor, the Fermi level is always lies between the center of the valence band and the conduction band. So then if the doping is increases, the Fermi level will be shut. So at that particular point, so this energy band becomes like a tunneling. So then the more number of charge carriers are rebelling from the so cathode to anode side to allow the maximum conduction. So that principle here is called as a tunneling effect. So define a negative resistance. So generally R means it is defined as the ratio of voltage to means what happens here if the V is increases or under Ohm's law V is equal to I into R. Or we can write I is equal to V by R means if the V is increases I is increases. So if it is a reverse process means either V is increases, I is decreases, or if I is increases, V decreases. So this type of the mechanism is called as a negative resistance. So list the applications of tunnel diode. So there are some applications. The tunnel diode can be used as an amplifier, either oscillator, or it can be also used as a switch. So up to this point in this session, we discussed that some of the definitions on FET amplifiers are also special purpose devices. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.